Okay, hi all. Hope you're doing well. Those in the Bay Area, good news is the smoke is now cleared, so we can enjoy some fresh air. So, last time we basically covered two things. The first of them was quantum teleportation. And basically, what that said is that if we wanted to send a qubit from Alice to Bob, but we didn't have the ability to directly do that, we could cheat and instead send two classical bits from Alice to Bob and use up one Bell pair's worth of entanglement, called one E-bit, and then we'd be able to use those things together, with a nice little quantum circuit in order to send our one qubit. And we also saw that there was sort of a reverse version of this, which is less interesting for practical purposes, called superdense coding, sometimes just dense coding. And in this case, we have, we're sending one qubit from Alice to Bob, and we're again using up an E-bit of entanglement, but in the process, we're able to send two classical bits from Alice to Bob. Okay, so today we're going to move on to talking about some more computer sciencey stuff. We've had a lot of physics background so far. It's going to be a bit more computer science background. None of it is going to be rigorous computer science background. I'm going to be shamelessly sloppy in all my definitions of what's going on. If you know, computational complexity theory and stuff, hopefully you can translate the things I'm saying into more formal statements. But if you don't, I think it's not worth us wasting a couple of lectures going into deep detail on it. But in particular, we're going to define some important complexity classes for different problems. This will include the famous P, NP, so like exp, P space maybe, the quantum version of P, which you call BQP, and so on. And in order to sort of define BQP and define what it means for a quantum computer to be able to do something efficiently, then we're also going to have to introduce the idea of a universal gate set. Which is roughly the quantum equivalent of the fact that in classical computing, if you can apply NAND gates, then you can use those to do anything, right? In this sense, the NAND gate forms a universal gate set for classical circuits. Okay, so what is complexity theory? You can answer this at various levels of precision, which sort of culminates in defining a Turing machine as a 7-tuple of various different objects, which I'm not going to do. But at the most sort of vague heuristic level, it's just a theory that lets you answer questions about how hard are problems to solve. So the most heuristic level, you'd like it to be able to tell you, for example, that the Riemann hypothesis is harder to prove or disprove than, say, the Pythagorean theorem. In practice, that's not something that you can really quantify. So what you can quantify is really how hard is it for a computer to solve a given problem if you know some particular algorithm. In other words, sort of how many elementary steps, whereby elementary steps, I could mean the sort of elementary steps of a Turing machine. It probably would mean that if I was being formal, but I could also just mean like number of logic gates I need to apply, assuming things are defined correctly, to solve some problem. Okay, so this is a sort of more precise quantitative notion. that we can like hopefully start to define things properly. But it's a bit too fine-grained, right? Like the question of exactly how many elementary steps it takes to solve some problem is going to depend an awful lot on exactly what you count as your elementary steps, right? Like if my elementary step is just a NAND gate, then applying an AND gate takes more than one elementary step, but I could also have my elementary step be, say, an AND gate or NOT gate, and then it's just one. There's a lot of different details of the definition will affect what the answers are. So that's sort of a bit too precise to hope to get a meaningful answer out of that we actually care about. So here's version 3. So these are getting sort of more precise as we go down. How does the number of elementary steps scale with the size of the problem? So for this, what we need to have is sort of a family of problems where you have inputs of different sizes. We'll see plenty of examples of them. Size of the input to the problem. And then we can ask questions about the asymptotic scaling of the difficulty of solving the problem in the limit where the input size becomes large. Okay. So there's a lot of different definitions of like classes of problems that you can define complexities for. But the sort of most common one is what's called a decision problem, which is pretty self-explanatory. What it means, basically what happens is you have some input that consists of, say, n bits, okay? And you're going to want to know how the difficulty scales with the number of bits. So this input goes into an algorithm, and the algorithm is the thing whose difficulty is scaling with the number of bits, where by difficulty, there's a whole host of things that could mean, as we'll see. And then we have just an output, which is going to be either, I'm just going to say it's either yes or no. Okay, could also say it's either 0 or 1, could also say it's either accept or reject. This terms doesn't matter, but the point is it's just a single classical bit that says whether, the input is it satisfies the decision problem or it doesn't. Okay. So then, we want to know the asymptotic scaling of the algorithm size, whatever we might mean by that, like maybe the number of steps, maybe something else, in the limit of large input size. We're going to call the input size n. Okay. So let's see some very simple example. An algorithm where you can actually, decision problem where you can actually determine the complexity, which is the following. The input is going to just be n bits. Okay. And then the decision problem is, does the bitwise sum equal 0? Right. So we're going to have these n bits of the input. And so it might be 1, 1, 0, 1, right? And then we just want to add up all those input bits. So 1 plus 1 is 0 mod 2, plus 0 is still 0 mod 2, plus 1 is 1 mod 2, and so on. There's two possible final answers. Is it 0 or 1? and we'll accept if the bitwise sum equals 0. Okay. Can anyone tell me what the sort of fastest algorithm that will do this is? How long that algorithm takes?
Log of the number of bits.
So you think it's log of the number of bits. So how would that algorithm work?
I don't know, like a tree sort of thing where you compare the first and the last, and then.
Yeah, so that's a good question. You might want to try and imagine a tree. So you could imagine, yeah. So you could imagine adding up like neighboring pairs of numbers, right? And then we add up the sums of those two pairs and so on. Okay. Here's my question. So we're sort of, in each step in the tree, in sort of each row of the tree, we're reducing the number of the sort of size of the remaining problem by half, right? But how many additions do we have to do each row of the tree, right? If I start with, say 8 numbers, so we have sort of 1, 1, 0, 0, 1, 1, 0, 1, right? Then we can add up these two, get 0, add up these two, get 0, add up these two, get 0, add up these two, get 1. Okay, and then we could add up these two, 0, these two, 1. Finally, add up these two and get 1, right? So we solved that, but how many additions have we had to do? Well, we had to do 4 in the first row, then 2 in the second row, and then 1 in the third row. So we've had to do we had 8 originally, so we've had to do n minus 1 additions. Okay, and actually that would generally be true for a tree, right? The number of additions you need to do in the first row is n over 2, and then n over 4, and so on. And so you end up with the total number of additions being n minus 1. So exactly the same, actually, as if you just did them in linear order going across. So in fact, the fastest algorithm for doing this takes order n time, right? Each of these additions, if you have to do an addition with NAND gates or something, it takes some number of NANDs, not very many, but like that's just some number that's independent of n, and then you have to do n minus 1 additions. So the whole thing is order n. And in fact, this is, you might think, okay, so that tree didn't work, but we could come up with something better. It's pretty reasonably easy to see that sort of any algorithm that solves this has to take at least order n time. And that's for the following reason, which is just to sort of look at each of these input bits, right, and do something with them, apply some sort of gate that like does something non-trivial with them, will take a order n amount of time just to read them all off. And if I haven't looked at one of the bits, then by changing that bit, I can always change the answer. And so I can never work out the answer without looking at all the bits. Okay. So this is the optimal algorithm. So this is called a linear time problem. Okay. If it was n squared, it would be quadratic and so on. But that was a particularly simple example. One of the first things to know about complexity theory is that it's generally very hard to actually prove that algorithms are optimal. And this is a source of a lot of the major unsolved problems in complexity theory, like the famous P versus NP and stuff. Often people are really quite convinced that something's not true and that there's not a way to do things. Find an algorithm that's sort of incredibly fast, faster than some bound, but it's really hard to show that it's impossible. So there's a question in the chat if that we assumed that addition for any sized number is order 1. No, we did not assume that. The point was that this is bitwise addition, so we're always just adding together 2 bits, right? If we were adding together larger numbers, then the time that takes is actually, it's linear in the number of bits of the number. Okay, good question though. So yeah, this is just a sort of general rule. And I want to give sort of an example of that to you guys, of something that is a very standard and important problem where the what people thought was the optimal approach for a long time turned out not to be. That's going to be, I was doing that in blue, wasn't I? Example 2. This is just going to be the task of multiplying two matrices together. So can anyone tell me whether multiplying two matrices together is a decision problem or not?
No, it's not.
Great. Why is it not?
Because you have multiple matrix. The output will be a matrix which has multiple entries.
Exactly. Yep.
They're real numbers or some numbers.
So yeah. So there might be ways you can convert it into a decision problem, but really, maybe we'll make the entries be integers or something. But it's still the case that your output is just a new matrix. So this is actually an example of something called a function problem. It's not equal to a decision problem. So this formally is not in the sort of complexity classes like P and MP and stuff like that. Normally formally are defined to refer to decision problems, but people will still commonly use those terms to apply them to things like function problems and stuff as well. And there are similarly defined complexity classes for function problems and stuff. Okay, so going to assume that the matrix is an n by n matrix, i.e. the size of my input is order n squared, right? We have n squared entries in the matrix. So anyone tell me the sort of standard algorithm? For matrix multiplication, how does the complexity of that algorithm scale with n? Let's assume that the number of bits of each entry of the matrix is like fixed. So multiplications and additions have some fixed cost. We're just interested in how the number of steps that you need to do matrix multiplication scales with the size of the matrices.
N cubed.
Awesome. It is indeed n cubed, right? So if I have matrix 1, matrix 2, then I have sort of n squared matrix elements that I need to evaluate, right? And in each case, I have to multiply together n pairs and then add them all up, right? So this, let's multiply with this, and then second with second, and so on. Okay, so each entry of the matrix takes an order n time to evaluate, and we have n squared matrices. It's an order n cubed algorithm. So back in the 1960s, this was the best known algorithm for doing matrix multiplication. Nobody had anything better than this. It seemed pretty optimal. Quite possibly, people would have naively assumed it couldn't be improved. Then in 1969, something called Strassen's algorithm was developed. I'm not going to go into the details of how it works, but you can look this up on Wikipedia. It's not too complicated. And this actually has a complexity that grows as n to the log base 2 of 7, right? So log base 2 of 8 would be n cubed. So we've managed to knock that down to 8. And in fact, that sort of spurred a whole industry of people trying to gradually improve the algorithms. And the sort of best known current ones are at about order n to the 2.373. Okay, so we knocked it down quite a long way from n cubed. The sort of, I think the still the best known lower bound is just n squared, just because that's the number of matrix elements that you need to evaluate. So or that there's the input size. So that's the number of things that you need to look at. But yeah, I think that the question of, I don't think many people think this is actually perfectly optimal. So the question of what's the most efficient algorithm to do matrix multiplication is still very open. Another example is just ordinary multiplication of two numbers. Yeah, maybe I'll put this as an example. Example 3. Just multiplication of n-bit numbers. And here, the sort of naive algorithm that you got taught in school takes, so we have sort of number 3, 5, 6, 4 times 7, 4, 8, 9. Okay, so to do this sort of standard algorithm, you'd multiply every pair of numbers together, right? You'd multiply 4 times 9, and then you'd add 60 times 9, and then you'd add 500 times 9, then 3000 times 9, so on. So the sort of standard algorithm is order n squared. It's actually only very recently, in the last few years, nailed down that you can actually get to n log n. They've sort of got very close to n log n for a long time, and they've now actually really nailed down that you can do it in n log n time. But the sort of important lesson of both these things is that neither of these optimal algorithms for matrix multiplication or for multiplication of large numbers ever actually used in practice. This is not because people are like too lazy to code it up or something. It's that for all practical purposes, they're actually slower than, formally less optimal. But actually faster because just the sort of constant terms, the overhead terms in front of this n log n that are independent of n can just end up being so huge that for the sizes of n that we're actually able to do, even on a supercomputer, then it's not big enough for the smaller asymptotic scaling to be able to take advantage of that. Okay.
Could you explain the difference between a function problem and a decision problem again?
Yeah, so a decision problem is, let's go back up here. We have an input that scales the size n. We apply some algorithm, and then the output is just like yes or no. Okay, so it's just a 1-bit output. For a function problem, then the output is basically a large number of bits. That's just a function of the input. I think you normally want the size of the output to scale comparably with the input, although you can vary that. Yeah.
I have a question.
Yep.
In terms of reducing the complexity, like by the order, do they find like in the algorithms, like do they find like redundancies in like the information, and like that's how they're able to scale down?
Yeah, basically. So this Strasson's algorithm, for example, it's really just a trick where able to evaluate like a 2x2 matrix in 7 steps rather than 8 steps. And then there's a way to like recursively apply that to like matrices within matrices. And that then gives you the scaling. And that's why it's log base 2 of 7. It's really just, it's just finding a way to like, not repeat stuff you've already done. Right, like with this multiplication, we're looking at all the numbers like lots of times and then multiplying them together in different pairs, but it's clear that there could be some efficiency savings there, right? It's not like this example here where we were literally only looking at the numbers once and they clearly needed to be used and looked at in some way, and so there's like no way it can be improved. Okay. So commonly there's sort of two types of algorithms that show up all the time. Commonly, algorithms fall into two buckets. There's a load of algorithms that are sort of polynomial in N. And, normally, in principle, polynomial in N could mean N to the million. Normally, in practice, the exponent is pretty small. I mean, it has to be order 1, so I won't write that. But it's like, let's say less than or equal to 3 or 4, something along those lines. Can be a lot bigger. So a good example of something that was a lot bigger is there was a recent thing where a undergrad doing quantum information called Ewin Tang managed to take a quantum algorithm that was thought to be exponentially faster than the best classical algorithm, and she found a classical version of that algorithm, a dequantized version of that algorithm that was only polynomially slower, but the scaling was like n to the 20 or 30 or something. I forget exactly what it was. But normally, even in examples where that's true, then people over time were able to optimize and they're able to decrease the sort of, decrease the power that n is being raised to. So these we sort of heuristically can think of as like fast algorithms for doing something. The other class tend to be exponential in n. I'm not saying these are the only sort of algorithms that exist. I'm just saying that for common problems you might care about, then they often are one of these two things. Okay? So the exponential in n is like worse than any polynomial. These are things that just end up being completely intractable for any significantly large value of n. Okay? So this leads to our definition of complexity class, P, which is just defined as the set of decision problems, although we can also, we also informally use it to define the analogous classes of function problems and other things like that. And it's decision problems that are solvable in polynomial number of steps or polynomial time. And it's polynomial with respect to the input size. Okay, and similarly, there's a complexity class called exp, which is larger, contains everything in P that are a lot more. This is decision problem solvable in exponential time. Okay, so it should be obvious that everything in P is also in exp. And similarly, we can define things sometimes called like exp, which is, exponential. By exponential time, I mean order 2 to the P of n for some polynomial P of n. Okay, so I don't just mean, could be like order 2 to the n squared or n cubed or anything like that. Similarly here is order P of n for some polynomial. Okay, so this exponential complexity class is really very large, but there's still things that aren't in it. And so, for example, we could define a class of problems that are solvable in doubly exponential time, i.e. time 2 to the n, which is really very, very huge. And generally, if your problem isn't even in exp, it's not even known how to solve it in exponential time, then you're probably not going to be solving it for n greater than maybe 2 or 3. Okay. So there's a lot of other ways to classify complexity classes other than just the pure sort of time it takes to do them. I sort of hinted at this earlier. So a natural example is what's called P space. This is the set of decision problems that are solvable using as much time as you like, but only using polynomial space, i.e. the sort of number of bits or the number of entries on the Turing machine that ever get used in the computation is some polynomial in n. Okay. It's a good exercise, depending on your background, to either just sort of satisfy yourself or to sort of try to prove first that anything that can be done in polynomial time can also be done in polynomial space. And secondly, that anything that can be done in polynomial space can always be done in exponential time. Okay, I'll leave you guys to think about that. You can ask me about it in office hours if you like or something. But the sort of final classical, well, there's a couple more classical complexity classes I'd like to talk about, but you can't talk about complexity classes without talking about NP. So someone tell me what NP is.
Non-polynomial time.
It's not non-polynomial time, actually. It's actually non-deterministic polynomial time. It's still, it like is polynomial time. It's just polynomial time with different rules. So we'll see that in a sec. So let's first see another example. Classic example of what's called an NP complete problem, which is the subset sum problem. Okay. This problem is the following. Given some set of n bit integers, input size is n times n. Each integer takes up n bits, and we have m of them. Is there some non-empty subset of those integers that adds up to 0? Okay. Simple enough. So for example, you could have 3 minus 5, 2, 7, 6. And in that case, 3 minus 5 and 2 adds up to 0. So the answer would be yes. You could also imagine like 5, 7, minus 2, minus 1, 6, 8. And in that case, there's no way to get them add up to 0. So the answer is no. So the fastest known algorithm for this problem when m and n are both large is order e to the min of m and n. Okay, in particular, input size is m times n. So if m and n are pretty equal in size, then this is like e to the square root of the input size. So this task is certainly not known to be in P. However, if I'm just super clever or very lucky, and I tell you an example of a subset that adds up to 0, then you can check it very efficiently, right? You just have to add up that subset. The size of the subset is most m, at least each consists of n bits, so the time it takes is just polynomial in m times n. Can check in polynomial time. Okay. So the class NP, which this is in, is going to be defined as decision problems that can be verified given some witness. By witness here, I just mean some like polynomial number of extra bits that tell you something useful. So for example, in this case, it would be the subset that adds up to 0, just a list of them. In polynomial time. Note, only need to verify the yes answers. Right, if the answer is no, if there isn't a subset that sums up to 0, then we don't necessarily have to be able to give you a way to check that none of them add up to 0 quickly. Actually, there's a different complexity class, or thought to be different, they may be equal, it's not known, called CoMP, that involves being able to verify no answers or find efficiently provable counterexamples. Verify no answers quickly. Okay, so let me slightly more precisely define what I mean by verify. So the witness, I'm going to call W. That's going to be some extra information that you get. So you get the input to your problem, and you also get some extra bits that are the witness. Okay, so the input would be the list of integers in the set, and the witness would be some subset that is claimed to add up to 0. Okay, and then you want there to be some polynomial time algorithm verifier called B. So this has to be polynomial time. Okay, and this V is going to say whether the witness is sufficient to prove that the input evaluates to yes. Okay, so in particular, you want that for any witness W, right, then if the actual answer was no, i.e. if Fi equals 0, answer is no, right? There's no subset that adds up to 0. Then for any witness, then this verifier will give the answer of no, the witness does not prove that the that input evaluates to yes, right? You want to have this verifier be impossible to trick, but you also want it to be able to have some witness that it trusts for any input. So for all inputs where the answer is yes, 1, you want there to exist some witness that you could give it, some subset that does add up to 0, where the verifier can say, oh, yep, that is indeed right. I trust you. That proves that the answer is yes in this case. Okay. So there's an equivalent definition. Which is actually the origin of the name non-deterministic polynomial time, which basically is the following. Allow multiple algorithms and just assume that you guessed, right? All the algorithms have to like work and give the right answer 100% of the time, but you assume that you just got lucky and guessed the fastest one, right? You just need one of the algorithms to work in polynomial time. So for example, the algorithms could just be test a random subset of the integers and hope that they add up to 0, and then try some others maybe. Okay, that's an algorithm that in principle, would not, for most inputs, any one of the algorithms would take like exponential time, but you could always get very lucky, right? For any problem, there'll be some subset that adds up to 0, and we could just imagine that we got lucky and just tried that one first. Okay, so I just say that to make clear that that's the origin of the name, but really this sort of, the efficiently verifiable definition is easier to work with. It's the way most people think about it. Okay, so it should be obvious that P is contained in NP, right? If I can just solve the problem in polynomial time, then I don't need a witness at all. I can just solve it. So that's fine. Clearly, I can also verify it with a witness. The P versus NP problem is about the fact it is unknown whether this is an equality. I really want to emphasize that the sort of consensus of experts in the field, whom I'm not one of, is that the answer is almost certainly they're not equal. And basically, it's just one of those things that is much harder to disprove than to prove. If you could come up with some algorithm for, say, solving this problem, the subset sum problem in polynomial time, then that would prove that they're equal. And NP contains a lot of stuff that would like transform the world overnight. It would sort of break the world overnight. Scott Aronson has some entertaining blog posts, if you go to his blog, about how if you prove that P equals NP, what should you do? And it's like a practical algorithm. And he's saying that you should like keep it secret, or you should publicly announce that you can do it, and just like let people send you problems, and then you solve that you would otherwise be unable to solve, and then you solve them efficiently. And then you just keep how you're doing it completely secret for like a year or two, just to like let the world come to terms with this so that cryptography doesn't collapse overnight and the world doesn't dissolve into anarchy. So in terms of math problems that would have an impact on the world, not necessarily a entirely good one, then it's pretty up there. Okay. But yeah, as I say, almost certainly not true. It's just very hard to like rule out the existence of some terribly clever algorithm that makes them be equal. So there's one final classical class that I want to mention, and that's what's called BPP.
Quick question about the NP
Yep.
that you defined. You said W, the sum of its bits was 0. Is that true?
Yeah, W. So the witness that would work for the subset sum problem is like a list of which integers add up to 0. Right?
Okay. Yeah.
So if you tell me a list of some that add up to 0, then I can check that that's true quickly, and then I'll know that the answer to the problem was yes. And for any case that has a yes answer, then there'll be some subset that adds up to 0, and so there's some witness that will let me solve the problem efficiently.
Okay.
I have a question.
Yep.
Can a functional problem be an NP problem?
Say that again?
Can a functional problem also be like NP?
Yeah, so yep. You can define an analog of the NP complexity class that's for functional things. So yeah, this isn't really a functional problem. It's technically a search problem. But the problem of if you have a large number, finding some factor of it, some factor and prime factorization of it, that's a NP search problem. There's also you can convert it into an actual like NP decision problem with a slight variation. But yeah, the sort of standard problem of find a factor is in the equivalent of NP, which is often also called NP for search problems.
Okay, thank you.
Okay.
I imagine you could turn any functional problem into a list of decision problems. Is that correct?
Yes, that should be if the output of the function is fixed size. So a search problem is different to a function problem because, say, in the factoring problem, there may be more than one right answer, right? A function there's a unique right answer. Yeah, but you'd really like to turn it into like one decision problem rather than like for the matrix example, right? The decision problem of find a certain matrix element, that's a lot easier than the functional problem of find the entire matrix. So they're not really like equivalent problems.
I see, thanks.
Okay. So BPP is roughly defined as follows. It's what's called probabilistically solvable in polynomial time. And by probabilistically solvable, I mean you're allowed to do some like stochastic algorithm where you choose your algorithm randomly, and you want that to give you an answer, and you want the probability of your error conventionally to be less than 1/3 in all cases for all inputs. Okay, so the fact that it's 1/3 is not terribly important, because, for example, I could just apply the same algorithm twice, or maybe do the same algorithm 3 times and go with the majority consensus, and then that will reduce my probability. I could do it like 100 times and go to the majority consensus, and then it will get, the error probability will get closer and closer to 0. The point is that it's some order 1 number that's strictly less than half. Okay, so there's another class called PP. I'm not going to write down, but that just means you need it to be strictly less than half, but it can be like a half minus e to the minus n, for example. It can be a tiny, tiny amount smaller than 1/2, and that makes it much, much bigger. So that means PP, for example, contains NP, because I can just like try some random witness, test whether that witness evaluates to 1. And then I always had some probability of having picked the right witness. And so the probability of accepting one that's true is slightly larger than half. And the probability of rejecting one that's false can be very, very slightly smaller than half. So technically I've sort of, I can do better than a random guess, but it's not actually solvable in the sense that I can't, with some linear increase in the amount of time it takes, solve it with high probability. Okay, don't worry too much about that. Just the point is that for BPP, you need to actually, you can't have it just be approach the probability approach half as n gets really big. It needs to be strictly less than some order 1 number less than a half. Okay, so again, it should be obvious that P is contained in BPP because they're the things I can do with error 0.
What is the B in BPP?
Bounded error. It's the fact that, the error is bounded by a third. So just PP is probabilistic, but the error can be arbitrarily close to a half. So again, unknown if these two things are equal. But in this case, the consensus is that quite possibly the answer is yes. So over the years, a lot of things there's things that are only known to be BPP, but not in P. But a lot of the big things have eventually been converted into a deterministic algorithm. And it's sort of the vague feel that the experts get is that this might be generally true, that you can always de-randomize them and get rid of the randomness required. Okay. So that is all I'm going to say about classical complexity classes. So what about quantum computers? Okay, so the first question we need to answer for our quantum computers is, what are our elementary operations? Right, what are the equivalents of sort of classical logic gates, or the sort of steps you're allowed to apply to a Turing computer or whatever it might be? Clearly, we don't want it to just be any unitary matrix acting on all our qubits. So in the circuit model, we define it to just be gates. Well, the first criteria is that we want all the elementary operations to be gates that act on a small number of qubits. However, you still have infinitely many different unitary matrices that can act even just on 1 qubit. So what we really want is just some finite set of elementary operations like you have for classical bits. But we want that finite set to be able to sort of approximate, to be able to build any unitary we want out of that set of gates. So it's a finite set of unitaries that generates any unitary. By generates, I mean that I can find some circuit built out of these gates that approximates any unitary to arbitrarily high accuracy. So in section 5.4 of Riefel and Pollock, it goes through in great detail how to implement arbitrary unitaries just using two things. Firstly, using arbitrary 1-qubit gates. So any 1-qubit unitary. And secondly, using CNOT gate. Okay, I'm not going to talk in detail about how this is done because I think it's like mostly unenlightening. It's just pretty mechanical process of trying to get the right thing happening to sort of every subspace of the whole Hilbert space. But the key point is that this is still using, arbitrary 1-qubit gates, so it still needs to be able to apply any one of infinitely many things, okay? So what we need is some finite set of 1-qubit gates that's universal in the sense that it lets us do any 1-qubit gate. Okay. So let's try a few attempts at getting some that will do the job. What's the most sort of obvious standard 1-qubit gate that we use all the time? Well, it's the Pauli matrices, right? So you might try using the matrices X and Z. But it's pretty easy to see that that's not going to get us arbitrary unitaries because applying either X or Z always preserves the computational basis, right? If we apply X to some state 0 or 1, we get some other state 1 or 0. Same thing if we apply Z, we still get a computational basis. So even if we link these two things together in some big circuit, then we're always going to end up with a computational basis state. We started with one, and that's certainly not true of general unitaries. So this is not universal. Okay. Attempt 2. Well, what's the main matrix we use to get out of the computational basis? It's the Hadamard gate, right? So we can try Hadamard, and maybe we want to keep up Pauli's because that was kind of useful, but we don't actually need both of them anymore because if we say have Pauli Z, then we can still make Pauli X by combining by X equals HZH, right? Because the H lets us switch between the two bases. Okay, so this is no longer going to preserve the computational basis, but what it does instead is it preserves Pauli matrices. What do I mean by this? I mean that, for example, for any Pauli matrix P, if I conjugate it with a Hadamard matrix, then I get plus or minus P prime for some other Pauli matrix P prime. And similarly, if I conjugate a Pauli matrix with Z, then I again get plus or minus P prime for some Pauli matrix P prime. Okay, and if I apply some general unitary, conjugate it with a Pauli matrix, then it's not equal to a Pauli matrix. It's just equal to some arbitrary matrix with eigenvalues plus and minus 1. So clearly this set is also not universal. There's actually a sort of nice, the set of gates on n qubits that preserve products of Pauli's, i.e. if I have unitaries such that U, P1, P2, so on, products of Pauli's on all the unitaries is always equal to plus or minus some other product of Pauli's, are called Clifford gates. They form a group, right? Products of Clifford gates are also Clifford gates. And in fact, all Clifford gates are generated by a set of just 3 gates. The Hadamard gate, the CNOT gate, and a final gate, which is called, which I'm going to call P pi by 2, sometimes called the S gate. I'm sticking with the book's notation. And this is just equal to 1 naught naught I. In other words, we have P pi by 2 squared is equal to Z. Okay, so it's a slightly larger group than we had in our attempt 2, where we used the Hadamard, the Z, and the CNOT gate. But yeah, you can replace the Z with this P pi by 2, and it still has this property. And it is a fact, an unfortunate fact from a quantum computing point of view, but not one I will prove. It's relatively easy to prove. Any quantum circuit built entirely out of Clifford gates is actually efficiently classically simulable. Simulable, is that even a word? Whatever, I'm writing it. So having these gates is not enough to do something interesting in quantum mechanical, something on a quantum computer that we couldn't just work out anyway on a classical computer. So we're going to need something better than this. And in practice, if you get anything in your gate set that isn't a Clifford gate, that's probably going to be enough. Or like Clifford gates plus anything that's not a Clifford. Particularly nice set of gates that people often use. It is a universal gate set, is the Hadamard gate, the CNOT gate, and what's sometimes called the T gate or the P pi by 4 gate, which is just like the square root of the P pi by 2 gate. It's applying a phase of pi by 4 if the state is 1. Okay, so this P pi by 4 gate is not a Clifford gate, and that is actually, you know, squares to P pi by 2. So you know, this can quickly generate all Clifford gates, but this gate set is actually universal. Okay, so any any unitary can be built out of these things. There's actually a theorem, moreover, called the Solovay-Kitaev theorem. That says any universal gate set of this form, i.e. with everything acting on a small number of qubits, can efficiently approximately simulate any other. Okay, so it doesn't really matter what universal gate set we use to define the elementary operations in our quantum computers, because as long as we don't care about some small errors, then any universal gate set can approximate any other. Okay.
Does approximately here mean to arbitrarily good precision?
Yeah, the precision is the sort of error is exponentially small in the sort of linear overhead. Like if I can approximate any gate in the universal so I have universal gate set 1, I want to approximate universal gate set 2. Okay, so the question is how efficiently can I approximate the gates in universal gate set 2? So I can do so with an error that decays exponentially with the number of gates that I use from gate set 1. So it's really very efficient. So what that means is as long as we only require a quantum computer to get approximately the right answer, then there's sort of a nice, well-defined complexity class for what that computer can do, which doesn't depend on the details of what unitaries are in our gate set, right? So this is called BQP. It's defined as decision problems solvable by a quantum computer in polynomial time with an error probability at most a third. Okay, so this is sort of the quantum analog of the classical computing class BPP. You could also define what's sometimes called EQP, exact quantum computer polynomial time. Where we're not allowed any errors, it's just things can solve exactly. But the definition is going to depend on the gate set, right? So it doesn't have the same, like there's arbitrary many different definitions depending on what gate set you choose, and there's no one natural preferred definition. So people basically don't ever talk about this. The natural class to talk about is BQP, the probabilistic version. Okay, so the final thing I want to talk about today is the following claim. Which is that almost all unitaries. So these gate sets are universal in the sense that we can approximate any unitary with like a finite circuit built out of these simple gates. But almost all unitaries require exponentially many simple gates. Okay, where it's exponentially many in the number of qubits. What this means is that if I want something to be in BQP, I want to be able to do it on my quantum computer pretty efficiently. Then, I can't just apply random unitaries to my n qubits all at once. That's just not going to be possible to do in BQP. Okay, so the art of quantum algorithms is finding unitaries that can be efficiently built out of simple gates. So let's just see proof of this thing. It's really quite simple. It's just a counting argument. So the first thing we want to count is how many different unitaries can we make using T simple gates. Anyone tell me the answer to that? One thing it depends on is how many gates I call simple gates, but I'm just going to call my simple gates are just going to be, say, this set of 3 gates, H, C naught, and P pi by 4. And we're going to be allowed to apply them to the H's, and the P pi by 4 can get applied to any of the n qubits, and the C naughts are going to be able to be applied to any pair of qubits. Anyone want to say answer to how many unitaries they think they can make? Okay, how many unitaries can I make with T equals 1?
2 to the T.
Great. So that is exactly the right scaling. It's going to grow exponentially with T. But let's just see a bit more precisely what happens. If T equals 1, well, there's 3 things I can apply. Okay. I can apply a Hadamard to any one of the n qubits. I can apply P pi by 4 to any one of the n qubits. Okay, so that gives me 2 n things. And then I can apply a C naught to any pair. So that gives a half n minus 1. So the total number of things I can apply is, I think it's a half n plus 3. We'll just call that n squared. Half n squared, maybe. I'll keep the factor at the front, but I'll not care about the 3n. Okay, what about if we instead have T simple gates? Well, we can just independently choose which one we apply at each step. So it's just this half n squared to the power T. Okay, so this is just order e to the order T log n. Okay, now we want to know how many unitaries we need to be able to make every unitary. Okay, and by make every unitary, I mean number of unitaries to approximate any unitary to epsilon precision. So I want sort of all the entries in the unitary to have an error at most epsilon. Okay. Well, the first question we need to answer is like, what's the dimension of the space of unitaries, right? So what's the dimension of the space of complex matrices acting on n qubits? Well, the matrices are 2 to the n times 2 to the n. Because the Hilbert space in n qubits is dimension 2 to the n. So that would be 2 to the 2n. But that's the complex dimension. So the real dimension is twice that. Okay. But then we also need to have the U dagger U is equal to the identity. That ends up putting, so U dagger U is positive. So it's always a real matrix, but we have 2 to the 2n constraints that all those matrix elements are equal to the identity. So the dimension of the space of unitaries is actually just 2 to the 2n. Okay, that's how many degrees of freedom I have to change the matrix elements of my unitary while keeping it unitary. Okay. Now what we want to do is we have this space of unitaries. So it has this very large dimension. And we want to be able to like make a net of unitaries in this space so that any unitary is epsilon close to some unitary in this net, some unitary in this grid, right? So the grid entries need to be order epsilon apart. So what that means is that the number of unitaries we need to make this grid looks like 1 over epsilon to the power of the dimension of the grid, right? We need 1 over epsilon points along each direction, and we have 2 to the 2n directions. So the total number of things looks like 1 over epsilon times 2 to the 2n. This is order e to the order to the 2n if we don't care too much about the epsilons. And now we just need to compare the sizes of these two things. And we find that t needs to be greater than or equal to, asymptotically greater than or equal to 2 to the 2n over log n. It's the number of unitaries needed to be able to approximate all unitaries number of simple unitaries needed to approximate any unitary is the least of order to the 2n over log n. Okay. However, the number of unitaries I can approximate grows exponentially with t. So if t is even slightly smaller than that, then almost all unitaries can't be approximated. I don't mean this in the mathematical p equals 1 sense, p equals 0 sense. Yeah, probably with 1 sense. I just mean in the limit of large n, then it will decay exponentially with n. It will be very, very tiny. Okay. So that is all we're going to cover today. Next time, we're going to finish off talking about complexity classes by showing that P is actually contained in PQP, i.e. that anything you can do on a classical computer, you can also do on a quantum computer. We haven't shown that yet, we will. And then we're going to see our first examples of quantum algorithms that are faster than classical algorithms of quantum speedups, so call them. Although they're going to be particular sorts of quantum speedups where you have what's called an oracle or black box, and you're wanting to minimize the number of times you call on that black box. That will all make sense next Tuesday. So thanks very much for listening. I will see you all then. And